Welcome back. In today's class, we are going to be dealing with conversion of order basis to base 10. But before that, there is something very important that we need to discuss. Basically, by definition, conversion from order basis to base 10 is the process that we know of changing a value from one base to base 10. That is to say, we are coming from one particular base, then we are moving to base 10. This is the implication of this definition. Don't forget that if you want to get any concept right, you must know the various parts of its composition. I told you when it comes to binary conversion, from order base to base 10, from base 10 to order base, then from one base to another. These are the three types of base conversion that we have. We have discussed the one that has to do with moving from one base to base 10. We have seen how to convert base 2 to base 10, base 3 to base 10, and base. And we have discussed the basic principle behind it. Now, what we need to do is to understand how to convert from one base to base 10, which is our standard base. But there is something that we need to tackle first. For us to understand this concept, what is this thing that we need to tackle first? The basic principle is positional value system. Positional value system. You know, when we are talking about position, we are talking about location. When we are placing a particular value at a location in a specific pattern, it refers to as positional value system. System can be defined as entity that is made up of more than one part. More than one part. Are you getting me? Or a specific way of doing things. This is also known as aka what? Place value. That is, put this particular value in a particular location. How does this thing has to do with what we want to do? You are going to say it. The implication of this is that every digit in a value does not ask the same weight. You must understand that. How do we mean by this? For example, 235 is a value. It consists of 3 digits. 2, 3, 5. Do they have the same weight? No, they do not. This one will confuse you. Another one is this. 555. Now you will see that this is same digit, but they don't have the same weight because they don't occupy the same position. So far, they are not on top of each other directly. So, what is the problem? What is the weight of this? What is the weight of this? What is the weight of this? What determines the weight of each of these digits is called place value. The value of the place where we insert this digit into. But this explanation seems to be somehow abstract. Where is the place? Where is the value? Come and look at it. Now, we want to deal with something in base 10. We have these 4 digits. Where is their place value? In numerical system like this, where you have this value, they don't write it. But you must know that they exist. This is it. Do you see that? Units, tens, 100, 1,000. Don't forget that we are dealing with base 10. What means is that each of these digits will have a standard scale of 10. But their precision will make the scale of 10 to be different. How do we mean? This is it. Can you see that? Now, the 1 in this place has 0 as para. The 1 in this place has 1, the 1 in this place has 2, this one in this place has 3. It actually means that the base, which is the scale by which we measure this value, it is the one that is actually determining where this particular number will be placed and what the value each digit will have. 10 to power of 3, that is 1,000. 1,000 is what? 1. So this is 1,000. 30 is 1,000. Why this one is what? 100. We have 1, then 20 is 100. This is 10 raised to power 1, that is 1 and single 0. Anything raised to power 0 is equal to what? 1. So at the end of the day, how do we determine the value of this? What they say by rule is that you must take this value and multiply it with this value. This is the place value of this. This is place value, which is 1,000 multiplied by 4. So this one sound what? 4,000. This one sound 4,000. Why this one sound what? 500, because it's in 100 position. This one is in 1,000 position. This one is 100 position. So we have what? 4,500. Then this one is what? 8 by 10, that is 10, that is 80, and 3 unit of 1, that is 3. If they want to pronounce it, they will say that 4,583. The question is, why do we put and in between 5 and 8? Who is the person that laid down the rules that after 2 digits from left to the right, from left to the right, you have to place and after the second digit? The fact is that there are some crazy things in nature. That's the reason why we have different society. For example, we have IUPAC society that determines the way you must name a specific chemical. That is the reason why you are a scientist. That's the reason why you are a mathematician. You belong to a specific society. In this society, there are standards. If you want to be part of the society totally, you have to follow the standard. The rules of the world actually determines what we have. Who are the people that set this rule? But normally, everything should be principle of absolute all or absolute none. Absolute all or absolute none. But this is principle of partials. Absolute all is mean that if you want to use and in this place, it should be 4,583. or absolute none, no and. It will be 4,583 without and. But this is a rule of partials. You put it someplace, you don't put it someplace. Who determine the principle? What is the rule that say that we must put and in between that place? This is the place you need to start to be reasoning like a scientist. Some people have established a rule. In your generation, you can come to say that those rules, we cancel it. It's not working. Are you getting me? So, but don't be a bad leader. I am not indulging you to be a bad leader. God will spell you. God will frustrate your life like frustrated mango. Don't frustrate people. Now, in this case, this is 4,583 because each digit has different values, has different position, therefore they have different weight. We must understand that. This is one example in base 10. Let us go to another example in base 10. Oh, this one has decimal position. So, what do? Can you see that? Okay, let me take my cleaner and try to clean up this so that you'll be able to see that. This class is an interactive class, so I am not going to rush so that you'll be able to get what we are talking about. So, let us see. Look at the pattern of arrangement. Something should be going on in your mind that what is the rule that determines this particular arrangement. So now, I want you to take something into your mind that after every large digit, if there is no decimal point there is a decimal point because decimal point end every number. Are you getting me? So the reason for this is that after this, everything else is what? Zeros. But this one, since they are not zeros, you have to put it. Are you getting me? So it actually implies that this thing is called 4,583.92. Not 92. Why? Jesus. God. Not 92. It is 0.92. Who determines that it should be 92, not 92? Okay, let's see. Maybe there is something that we need to figure out here. Wherever you see decimal place, are you getting me? Place 4 cardinal points in that place. Are you getting me? Which is Cartesian coordinates. Okay, Cartesian coordinates. So it increased along this direction. It increased along z direction. It increased along z direction. It increased along z direction. But this direction is negative. This direction is positive. This direction is positive. This direction is negative. So at this point here, everything that we have is 0, nothing else. So it increased outsideward. So it will be 1, it will be 2, 3. Then this one will be 1, 2, 3. This one will be 1, 2, 3, 4. It used to be like that. So 1. So that is that for that. This is how the thing is arranged. If you place the 4 cardinal points. So to the 4 cardinal points here, what do we have here? So what they do is that this one here is in position of 0. If you look at that position, so this one that is in position 0 here, are you getting me? So it's allocated to this. Okay, why this one? It will be 1, then it will be 2. Can you see that the number in power here continue in that direction? Why the number in power here, they also continues in this direction? Are you getting me now? Now, what we are having in this case is that after decimal point, every number is a fraction. That is inverse of what is in this place, because this place is opposite of this place. So when something is opposite, we have inverse. So, but in this case, it is not additive inverse. I told you, go and watch the video of additive and multiplicative inverse. This is multiplicative inverse. So if we have 10 raised to power 3, the inverse is going to be 1 over 10 raised to power 3. So that's the reason why all this place is inverse of what is in this place. So why are we now having 0.02? This place is clear to us. We have known what is in this place, 4,583. But what is this one here? This one is equal to what? Is 0.1. Yes. This one is what? Is 0.01. So if I multiply this one and this one, I'm definitely having is 0.9. Are you getting me? Then I'm having is 0.02 for this one, because I'm multiplying this with this. I'm multiplying this with this. Now let us now come to see the crazy rules of the world, where there is deviation from what they call standard as a rule. If we call this one 4 multiplied by 1,000 is 4,000, then multiplied by 0.1, is it not supposed to be 0.9? God of universe, I want you to see some things, because you are learning in new dimensions, to identify what is the problem, to put your state in the minds of the people that actually do this, that this is the standard we are going to be using in the world to count numbers. So if this one is 4,000, this one is 500, which is correct. Are you getting me? What happened to this? This one should be okay. Let me say I want to pronounce this one. It should be 4,583.0.9 and 0.02. That should be the correct pronunciation. Why are they now saying that we should not call it as 0.9, 0.02? Why 0.02? Why? I will tell you the reason. Honestly, I will tell you the reason. 10 is standard base. In its actually normal directional form, it does not change the value. It does not change the value of each digit. It does not change the value of each digit. If you look at 4,000, there is still 4. 500, there is still 5. 83, there is still 8. And 3, there is still 3. So if that standard is maintained, so the pronunciation of this one also should maintain the standard. But because of the fact that we have fraction, we should call each individual digit all along. That's the reason why they made it like that. But you cannot understand what I'm talking about until I give you an example of comparison. So now, this is everything about base 10. Are you getting me? Let us now go back and look at what we have inside the base, other base. Are you getting me? So what do we have inside other base? Let us look at base 2 now. We want to do the same thing in base 2. So we have 1001. Because we are working in base 2, every digit inside base 2 must be less than 2. Are you getting me? That's the reason why we are having only 2 numbers to work with in base 2, is zeros and 1. So what is place value of this? I am just giving you a rule. This one does not exist. I'll say that, okay, if they have unit tens, which is unit is 1, tens is 10, 100 is 100, 1,000 is 1,000. I say I should have unit for 1, I should have bi for 2, I should have tetra for 3, I should have octa for 8. This is my own innovation. This is my own thinking. Are you getting me? Because there is no equivalent for base 2. Now let us now see the place value. The place value is this. You remember that the scale, are you getting me, and the position of the particular number. The scale and the position of the particular number. So this is the scale, which is base 2, and this is the position. Let us now look at this. This is 1 times 8. This should be 8. 1 times 4, this is 4. This is 2. This is 1. By standard of pronunciation, if you want to trace the same pronunciation as this number here that we are calling 11 is 01 as individual number, if you want to call them the way they should be, it is 84 and 21. 84 and 21. Remember the hand between the 2 digits here. So it should be 84 and 21. So the pronunciation of this number is what? 84 and 21. there is something wrong in this. You will see that normal human brain cannot process this naturally if you don't do computation. Any other basis aside from standard base, which is base 10, will actually change the pronunciation of every number in their actual place value. Go and try it with base 3, go and try it with base 4, go and try it with base 16. You are going to see the same thing. Are you getting me? So the fact is that this is the pronunciation of this one here. But we just keep to say, call them one by one, 1, 0, and 1. But the actual pronunciation by the same template that we used to establish this is what? 8, 4, and 2, 1. You can see that it has totally changed. So you can now see the reason why we are using base 10 as the standard base. It is the only base that does not alter the true identity of each digit in their place value. Any other base actually does change the value. So this is another example, just like for our own decimal. We have decimal also in source order in other place value. So I use the same templates as for the place value. Then this is everything here. So you can now see what we are trying to imply in this place. So this one is what? 8, 4, and 2, 1. Sorry that I don't write it corresponding to each other vertically. Sorry for that. So 8, 4, and 2, 1. What will be this? This is equal to what? 1 divided by 2. 1 over 2. That is half. That's 0.5, right? 0.5. 0.5 should be what? Is 0.5. Are you getting me? Isn't it? Yes. It should be 0.5. So if we now look at it, if you will be able to see something that is very obviously crazy. And what is it in that aspect is that you are trying to do the same template pronunciation as that to our base 10, you are going to see something crazy. So let us finish everything. This one is what? 0.25, right? Yes, this one is 0.25. So what are we going to say? We said 8, 4, and 2, 1, 0.525. 0.525 or 0.52. You see, you don't think too far when you are studying a specific phenomenon. That is the reason why you don't see the crazy aspect of that phenomenon. People who are discoverers in this universe, they are people that think crazily beyond the box, out of the box, as in they just think that what should happen if this thing is there. So between you and I want you to write it in comment section. Should there be any reason for us to choose any other base aside from the standard base 10? If there is any reason, put it in your comment section. Let's start research. Maybe we are going to write something to the scientific community in the world, and this is what we come with from LBP Society. Let us see, let us scatter ground, let us give them proof. If it's going to be possible. Yes, we didn't say this is not possible. If you have a concrete evidence for that, scientists will believe in experimentation and evidence. So as a scientist, you have seen the new dimension of number bases. So this is the standard that we need to know first before we learn how to convert from other bases to base 10. So for this is where we're going to stop today, because I don't want to, this is interactive class. I don't want it to go too long. So please subscribe, follow, comment, like, and share. To that UTME student, to that WAEC student, to that student preparing for mathematics outside Nigeria. This is mathematics. It is the same thing all over the world. So far you can understand English language. You don't have any problem tackling this. This is number-based conversion. Thank you for listening. ABP.